Hey everyone, in this video we're going to talk about section 6.3, which is about graphs of polar equations. Before this video, you should have already completed the Desmos exploration and written down your observations of what the different coefficients mean for each type of graph. In this video, we're going to go back and we're going to learn how to graph each polar coordinate by hand, and we'll discuss what observations you should have maybe noticed during that exploration. So again, polar coordinates are really helpful to us because they allow us to graph shapes that normally would have very complicated equations in the Cartesian form. The main polar graphs we're going to be looking at are a rose curve, circle, a limousin, spiral, and a lemniscate. So we're going to start with the rose curve. Okay, so rose curves are defined by having some sort of coefficient A. We're talking usually about sine or cosine, and then they have a coefficient in front of theta as well. So that A coefficient represents a stretch, which tells us how long those petals are. B tells us a couple of different things. So first, if B is odd, that represents the exact number of petals we have. Or if B is even, then 2B, or twice that B value, is the number of petals. So for instance, like if we had, if B was equal to 2, we'd have 4 petals. Okay, if B was equal to 6, we would have 12 petals. Okay, that B value also tells us the type of symmetry we're going to have. So if B is an even number, we're going to have polar or origin axis symmetry. Okay, so reflection over the origin. But then if B is odd, depending on the function, it has a different type of symmetry. So if B is odd and we are talking about cosine, we're going to have reflection across the x-axis. And if B is odd and we're talking about sine, we're going to have that reflection or that symmetry across y. And then depending on this function that we're looking at, that tells us where our first petal is going to be at. So if it's cosine, our first petal starts at 0. And if it's sine, our first petal is going to start at pi over 2b. Now, this first petal fact is not something that's something that needs to be memorized. We're going to talk about how to generate those points differently. Or a way to generate those points, I should say. Okay, so in example 1, we're going to graph the polar curve, and then we're going to state the exact values of key points in polar coordinates form. So we're going to look at r equals 5 sine of 3 theta. So before we even begin to graph this, knowing what the function is and knowing what we know up above, we should be able to kind of picture or predict what's going to happen. So first, the number that we have in front, okay, that A coefficient is 5, so that tells us that our petals will be 5 units long. Okay, we are talking about sine, okay, so that should tell you a little bit about where our first petal should start. It's also going to tell us about our symmetry. I see that we have a 3 in front of that theta, so that B value is odd, so I know we're going to have 3 petals. And then in addition, because it's odd and we're talking about sine, I know that we are going to have y-axis symmetry. Okay. One thing to note, again, just with a polar graph, I say x-axis symmetry, y-axis symmetry. In a polar coordinate system, we don't really have x and y-axis, but I'm still just talking about like where the normal x and the normal y-axis should be. So that should at least give you, we can still think about this in 4 quadrants, so that should still tell you a little bit about like where we're gonna have that symmetry. Okay, so for this, first, remember that polar coordinate form means that we're going to write all of those points in terms of r's and thetas. Okay, so theta is our input and r is our output. Now, to come up with our key points to graph this, we're actually going to revert back to what we talked about last semester when we first started learning about the trig graphs. Okay, if this function had been written as y equals 5 sine of 3x, we would have known how to create a sinusoidal curve to represent that. So we can still take those points from that sinusoidal graph, but this time we're just going to convert them to be in polar coordinate form, and then we're going to graph those. Okay, so let's graph this function. Okay, so I'm going to create some axes below. Okay, a couple of things that we should know about this. Okay, so we know the amplitude is going to be 5. Okay. We know what our period is going to be, okay? So we know that our B value here is 3. So we know that our period will be 2 pi over B. So our period is 2 pi over 3. So if we're going to go graph those points, usually what we did last semester was we divided that period into 4 to get where our key points are going to be. So this is going to be 2 pi over 12. So we are going to have a point every pi over 6. Okay, so let's graph some of these points. Pi over 6. 2 pi over 6 will be pi over 3. Let's see, 3 pi over 6 will be pi over 2. Let's see, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6 will be 2 pi over 3. And that's our period. Okay, so we're going to start with these points, and if we need to add more later on, we're going to do that. Okay, so now we know that this sine, we don't have any shift of the midline, and we know that sine starts at the origin. Okay, sine starts low. So my curve is going to look like this. Okay, so using those key points that we had, we are going to convert these to be inputs of theta and outputs of r. So for each of these points, the x-coordinate or the input coordinate will be the theta, and then the output coordinate of where it ended up will be how far out on the radius we'll go. Okay, so we're going to start first at this point here. Okay, so our input theta was 0, and our radius that we got out was r. So that's going to be this point here. Okay, so that's where we start. And that should make sense to us. Cosine starts, wait. 2 pi. Oh, wait, okay, the first petal starts. Okay, never mind. We'll get there. I'm a little ahead of myself. Okay, so that's my first point. Okay, my second point, I'm going to go out pi over 6. Might be helpful if we label this. Okay. Okay, so going out pi over 6, so we're going to go out 5 on our radius. So that's going to be this guy here, okay? Then we're going to plot this point next. So for pi over 3, we're going to have a radius of 0 again. Now you're going to notice that that just overlaps this point. Okay, so what our polar curve has done is our polar curve has done this in pi over 3. Okay, next point we're going to graph is a pi over 2, and our radius will be -5. So pi over 2 is up here, but we want to go 5 in the opposite direction. So we're going to be down here. Okay, so what our polar curve has done is we have gone here. Excuse me. Okay, now for 2 pi over 3, we are back at 0. So 2 pi over 3 was right here, and we've gone to 0. Okay. Now you may be thinking to yourself, well, hold on, we were supposed to have 3 petals. And you're right. So one thing to note is that the period of a polar graph does not necessarily match the period of what the sinusoidal graph would be. So our sinusoidal graph's period was 2 pi over 3, but for our rose curve, our period is actually going to be larger than that to complete the entire curve. So let's just add a couple of more points until we can graph the entire curve. Okay, so I might graph maybe another period. Let's see how many of them we need. Okay, so let's see. So this guy would have been 4 pi over 6. So this guy will be 5 pi over 6, and then we'll have 6 pi over 6, so that'll be pi. Okay, let's just go a couple more. Okay, so for 5 pi over 6, that's here. Okay, we have a period, it looks like our radius is 5. So let's see, 1, 2, 3, 4, 5. Okay, so we've gone out here. And then at pi, we have a radius again of 0. So we are back here. Okay, and it actually looks like in this case, our period is equal to pi, okay? Because let's see what would have happened if we kept going, okay? If I had plotted this point, okay, this would have been 7 pi over 6. Okay, we would have had a radius of -5. Okay, so 7 pi over 6 is this here. Okay, and we would have gone backwards 5. Well, that would have just graphed here again, okay? And so we would have started retracing over that. So the period of our rose curve was pi. Okay, we said we were going to come up with a couple of points. So let's just plot where some of those points are. Okay, so we had a 5 pi over 6 here. This point at the origin represented several different points. Okay, this was 0, 0. This was also, let's see, 0 pi over 3. This point was also, running out of room, 0 for our radius, and 2 pi over 3. Okay, this point, or hold on, we went to this point next. This point was pi over 2. Nope, hold on, radius first. This was negative 5 pi over 2. And this one over here was 5 pi over 6. Now, you might be thinking to yourself, okay, hold on, do we have to name every single point? No, but we're still just trying to get across what our polar coordinate form of those key points are. So really, this graph here states where all of our key points are. It's just good to know how they show up on our polar graph. Okay, something else that can sometimes be helpful, and this will be helpful to us next year in BC. It is good sometimes to put some arrows on your curve just to denote the way that that curve was growing. Okay, when you see the final thing, you don't really know how it graphed itself and how it curved, but putting those arrows can help you kind of follow that pattern. All right, okay, so that's going to wrap up our rose curve. The next one that we're going to look at is the circle, okay? So hopefully for the circle, you saw a couple of patterns with it. Okay, so first, if we looked at r equals a, our graph looked like this, and you'll notice that that a represented the radius, okay? And your circle was centered at the origin. Now, if we had r equals a sine theta, we saw that that center was no longer at the circle was no longer centered at the origin, but now its center was somewhere on that like y-axis, okay? You'll also probably have noticed that a no longer represented the radius, but a was now the diameter. Okay, and then for cosine, same thing, a is going to represent our diameter, but this time the center of that circle was on the x-axis. So that kind of follows along with some of our other functions that we've looked at and where that symmetry occurs. Okay, so for example 2, we're going to state it by hand. We're going to graph it by hand. We're going to state some of those key points. So what we're looking at is we're looking at r is equal to 4 cosine theta. Okay, again, we should be able to picture what this looks like. So we know that the diameter will be 4. Okay, and then because it's cosine, we're going to have x-axis symmetry. Okay, depending on if a is a positive or a negative value as well, that can also affect where it shows up. Because a is 4, okay, and it's a positive number, I know that we are going to be in like quadrants 1 and 4. Okay, so honestly, we don't even really need to plot the points to be able to graph this, but I still want to go through that exercise of figuring out what those coordinate points are in order to graph. But we have a good visual as to what this will look like. Okay, it's going to look like this. Okay, again, if this had been written as y equals 4 cosine x, we would have been able to graph this easy peasy last semester, so let's use that graph to generate our points. Okay, this cosine graph has an amplitude of 4, and there is no coefficient of x except for 1, so that means that our period will be 2 pi. Okay, so all of our points that we're going to graph are going to go in pi over 4s. So pi over 4, pi over 2, 3 pi over 4, pi over 2s. What am I saying? Because it's 2 pi over 4, which is pi over 2. Okay. Sorry. All right, and then cosine we know starts high or low. So our cosine graph looks something like this. Okay, and then we know that that 2 pi might not exactly be the period of our polar curve, so we'll just graph as many points as we possibly need. Okay, so for this, our original theta, okay, was 0, but our radius is 4. Okay, so when we start at theta 0, this is here, okay, but I'm going to go out 4. So my first original point is here. That's 4, 0. Okay, my next coordinate point here is going to be pi over 2 for my theta, which is here, but now my radius is 0. So that's going to be this point here. Now, if you think about it, you're like, okay, well, did I just draw a straight line between it? No, remember it's going to be a circle. Okay, so one thing that might be helpful to us is to come up with one more point in between to graph. And this can just be helpful just to kind of visualize it. I always recommend, let's choose the value. Okay, so that could be, pi over 6, pi over 4, pi over 3, something in there that's going to give us not a radical so we can easily multiply that number. Well, I know that for cosine of pi over 3 is 1/2, so pi over 3 is probably the best like in-between point to choose so we can multiply, okay? So for pi over 3, I know we get a half, so when I multiply that by 4, we're going to get out 2. Okay, so this point is pi over 3. 2. Okay, and again, I know that my polar coordinate, I'm going to have to rewrite that, but it is what it is. Okay, so for pi over 3, which is here, I'm going to go out 2. 1, 2. Okay, so my curve is graphing this way. This is 2 pi over 3. All right, we'll keep going. My next point that I have will be down here. Okay, so for pi, my radius is going to be -4. Well, here's pi, and then going backwards -4, I am here. So actually, that was horrible. Okay, our polar graph looks something like this. So again, our period did not match what the trig function was, but our period was pi. Because we got back to where we started. And I know that if we kept going, we're just going to keep graphing the same points again. Like if I graphed 3 pi over 2, which is down here, my radius would be 0, so I would have just continuously graphed in this little loop. All right. That's our circle. Let's flip over a page and we're going to talk about our spiral next. Okay, so for the spiral, as it is aptly named, we know that it looks like this, okay, and it keeps spiraling out. So it only has one coefficient. That coefficient is A. That A is representing a stretch of just like how tight or how loose our spiral is. So if A is greater than 1, it's going to be a stretch. Okay, it's going to really like, imagine a spring, right? Like I'm stretching that out. If A is a number that is in between 0 and 1, it's going to be a shrink or compression. And if A is negative, that's just going to represent a reflection of how it spirals out. Okay, so that absolute value of A is really what's going to control the shrink or the compression. Okay, so we're going to graph r equals 4 theta. Okay, so I can see that here our stretch is going to be 4. Okay, so it's really going to kind of be like a loose spiral. Okay, when we go to graph this, you're probably thinking to yourself, well, that's not a trig function that we've graphed. You're right, it's not. Okay, but we have graphed other functions like this. Maybe not in pre-calc, but you have somewhere. Imagine this as y equals 4x. So when we come up with these points, we're going to be thinking about this linearly. You can do this with a graph if you want. You can also use a table. Honestly, a table might be easier, but we're going to do a graph. Okay, so coming up with this, we want to come up with some thetas that are going to give us an output of our radius that we're going to graph. When we come up with those thetas, again, probably for ease of wanting to come up with points that are going to multiply nicely, let's maybe choose some values that multiply by 4 nicely. We want our theta values to also, again, be in radians, so I don't want to call this, 1, 2, 3, 4, because that doesn't really help me graph my radians nicely. So maybe let's call these, I don't know, pi over 4. That'll graph pretty nicely and multiply 4 nicely. Let's see, pi over 2, 3 pi over 4, pi. We can keep going. Let's just maybe start with 4. Okay, so this is going to be linear. So I know that my points are just going to look something like this. Okay, now we need to find out what those outputs are. Okay, so if I plug in pi over 4 here, okay, pi over 4 times 4 is just going to be pi. Okay, if I plug in pi over 2, it's going to be 2 pi. If I plug in 3 pi over 4, that's going to be 3 pi. If I plug in pi, that's going to give me 4 pi. Okay, that's a good place to start. Now, we need to go ahead and graph those. I can see here that my radiuses are in terms of pi. Well, honestly, this could be pretty good. Our polar graph that I see actually does not have the circles labeled for us, so I think we can call those circles whatever, we can call those this concentric circles out whatever we want. So let's go ahead and label it. So let's label this maybe pi, 2 pi, 3 pi, and 4 pi. Okay, let's start graphing some points. So when theta is 0, my radius is 0. I'm going to start here. Okay, when theta is pi over 4, okay, that is the same thing as 45 degrees. We are at pi. When theta is pi over 2, okay, we get a radius of 2 pi. It's going to be up here. When we were at 3 pi over 4, our radius was 3 pi. That will be here. And then when our theta was pi, we were at 4 pi. So that is here. So when we go to graph this, we are graphing out like this. And you're probably thinking, well, that was pretty boring, okay? But think about what's going to happen as we keep going around, okay? Let's say that we went to 5 pi over 4. And then we went to 3 pi over 2. Well, what's going to keep happening? Well, I know we're just going to keep, going around linearly. So, I would need another concentric circle to do this, but I'd probably be out somewhere here, then I'd probably be out here. So I see that my spiral just keeps going out farther and farther, and then we're just going to keep going around like this. Okay. So that's what our spiral looks like. It just linearly spirals out. Okay, labeling a couple of key points. This was 0, 0. This was pi over 4. This was pi over 2, 2 pi. This was 3 pi over 4, 3 pi. And this was 4 pi. Ooh. I wrote these backwards, hold on. Okay. 2 pi, pi over 2, 3 pi, 3 pi over 4, 4 pi, pi. Okay, there we go. There's our spiral. Next one that we have is going to be our limacon, okay? Limacons have this form, okay? So A plus or minus B times sine theta, or R equals A plus or minus B cosine theta. Now, I already went ahead and just wrote in those observations for you, because honestly, depending on the A and the B means so much can happen. Okay, so honestly, what we need to do is we need to compare which of those variables is larger, if A or B is larger, if they're equal, one's smaller than the other, etc. Okay, so if A is less than B, we end up with an inner loop. Okay, we end up with this kind of spiral on the inside. It loops back within itself. Okay, if A and B are equal, this is going to be a cardioid. We end up with our point at the origin. Okay, so it kind of looks like a heart. And then if A is greater than B, okay, so the value that we're adding onto it, not the coefficient, if A is greater than B, we end up with we either call it a dimpled limacon or an oval limacon. And it kind of pulsates out. It kind of looks like a tomato to me. Okay, we also have certain symmetry depending if we're talking about x or y axis. So again, sine is going to have y axis symmetry and cosine is going to have x axis symmetry. So in example 4, we are going to graph and state, again, the exact value of key points in coordinates and polar coordinate form. So we have r equals 3 minus 5 sine theta. Okay, let's predict what this looks like. Okay, so I see here that A is less than B, okay, because 3 is less than 5. So this guy is going to have an inner loop. Now, you will note that we are subtracting it here. So in this case, that is going to make our symmetry go down. So we're going to be in quadrants, most of the time we're going to be in quadrants 3 and quadrants 4. Okay, again, to graph this, we're going to come up with our our coordinates if we were talking about y equals 3 minus 5 sine x. All right, so let's graph this. Okay, well, what would we have known about this? Okay, so I see that my amplitude is going to be 5, but I see that my midline is not going to be y equals 0, it's going to be 3. Okay, so that means if my amplitude is 5, my max and my mins are going to occur at 8 and then at -2. Okay, so here's my midline. Okay, I don't have a coefficient on x except for 1, so that means that our period is going to be 2 pi. So we're going to come up with points every pi over 2. All right, okay, it's sine, so I know that we're going to start in the middle, but we are subtracting, which means that we're going to have a reflection. So instead of going high first, we're going to go low. Okay, we're going to start with those. If we need to add more points, we can definitely do that. Okay, so thinking about this in terms of thetas and resulting r's, when theta is 0, we start with a radius of 3. Okay, so here is 0, radius of 3, 1, 2, 3. We'll start right here, okay? So interesting, we started somewhere, not the origin. Okay. When theta is pi over 2, we have a radius of -2. So we are here. Okay, so you're going to notice something happened, okay? So how did we go from here to here? Let's find another point that's going to go kind of in the middle of this to graph, okay? So we're talking about sine, so I know that sine of pi over 6 is going to be equal to 1/2. Again, that's like that output that it doesn't have a radical in it or a square root, so this is going to be something that we can easily graph without needing a calculator to approximate it. Okay, so if I were to plug in pi over 6, I would have 3 minus 5 times 1/2. Okay, so that's 3 minus, let's see, what is that, 2.5, which would be equal to 0.5 Okay, so let's see. At pi over 6, we would have been at 1/2. Okay, so let's graph that point too. So here's pi over 6, and we're going to go out half. Oh, it's going to be so small. It's going to be in there. Okay, so what does that tell us is happening? Well, what we're doing is we are going here, and then we are looping back down and around. And if you need to think about another point, if you need to, for right now, pull out your calculator to double check and see what's happening here, we're going to see that we're going to end up with negative radiuses because 3 is going to start subtracting things that are larger than 3, which is going to give us a negative radius. So for these values here, we are going to be going backwards, okay? So this is where I see that inner loop forming. Okay, plotting our next point, we're going to pi. My radius, again, is going to be 3. So I have looped out here for 3 pi over 2. That's this guy here. We have a radius of 8. Okay, so I'm going to count out 8. So here's -5, 6. Okay, here's 8. Okay, so it looks like our curve has gone here. And if we wanted to find a point kind of in between to make sure we know how far out it's going, let's maybe choose something in between. Again, let's maybe choose one of those pi over 6 multiples, maybe 7 pi over 6. Okay, so sine of 7 pi over 6 is equal to, let's see, -1/2. So we would have had 3 minus 5 times -1/2. Okay, that's 3 plus 2.5, which is 5.5. So for this here, we are at 5.5 as our radius. So that would be here. Okay, so it's really gonna kind of loop out. So it's pretty wide. And then it's gonna come out. And then I see that we're gonna actually just end up having some symmetry. So it's gonna loop all the way back in here. And I know that's gonna happen because when we go to 2 pi, again back here, we have a radius again of 3. So our graph ends up looping like this. Okay. Something that is helpful just to note and something to keep in the back of your mind is that symmetry portion of it. So when we go to graph it, once you have half that graph, we know in this case it's going to reflect across the y-axis. We can just graph the other half of this curve. Okay. All right. I think we have one more graph that we're going to look at. Okay, and that's our lemniscate. All right. Our lemniscates are definitely interesting, and they're definitely different. So the form of them is r squared equals a squared sine of 2 theta, or r squared is equal to a squared cosine of 2 theta. What they end up looking like are infinities. Okay, so depending on either if that a value is positive or negative, and if we're talking about sine or cosine, that depends on where our graph ends up. So cosine is either reflected or has symmetry over the x-axis or the y-axis. Now, if a is a, positive number in front of it, meaning that we don't have a negative out in front, it's going to have x-axis symmetry. Or if it has a negative in front of it, then we're going to have y-axis symmetry. Okay, now if our graph is a sine graph, we're going to have symmetry not over one of the not over one of the axes, but we're going to have symmetry over equals, or like y equals x or y equals negative x. Okay. Now, when we go to graph this on a graphing calculator, you're going to have a difficult time doing so because of that r squared. Okay, so if we're going to graph it, we have to take the square root. Okay, so we're going to either graph r equals a square root sine of 2 theta or r equals a square root of cosine 2 theta. And that's because if we start with that r squared, so we have a squared sine 2 theta. Okay, and when I go to apply that square root, we can take the square root of the a squared, which becomes a. We can't take the square root of the sine 2 theta, so that's why that ends up underneath that square root. And technically, yes, we do end up with a plus or a minus. What that plus or minus just does, though, is change the direction in which we graph. We end up with the same curve, we just end up going a different route about it. Okay, and then one thing that I didn't mention yet is that a just represents that stretch. So that just ends up representing, I want to say maybe the radius, okay, how far out, like the propellers or the infinity, loops end up going out. Okay, so in example 5, we're going to graph and state the key value, the exact value of key points of r squared equals 4 cosine 2 theta. So we know a couple of different things about it. First of all, a is equal to 4. 4 is equal to 2 squared. So those propellers or those loops are going to end up having like a length of 2. 4 is also a positive number, and we're talking about cosine, so our infinity is going to look something like this. Okay, so it's going to have that x-axis symmetry. Okay, we, again, are going to graph this curve. However, when we graph this curve, we are really graphing y squared equals 4 cosine of 2x. Okay, which means that we're really going to be thinking about the graph of y equals 2 square root of cosine 2x. Okay, the video got cut off, so let's just pick up where we left off. Okay, so we are graphing, or coming up with the key points using the graph of y squared equals 4 cosine 2 theta, which, if we take the square root of it, is y equals 2 square root of cosine 2x. Okay, we haven't talked about taking the square root of a trig function and what that looks like. However, we can still come up with those points based off of if this wasn't y squared. So let's first graph y equals 4 cosine 2x. Okay, we know that this has an amplitude of 4. Okay, we know that its midline is 0, and we know that because 2 is our coefficient on x, our period will be 2 pi over 2, which is pi. Okay, so that means that we're going to graph points every pi over 4. Okay, so we know that this graph looks like this. Okay, well, now we're not talking about that graph, right? We are talking about, if this was y squared, we're talking about the square root of this, okay, which ends up being 2 square root of cosine 2x. So first of all, our amplitude that we have ends up being square rooted. So our amplitude is now going to be 2 and negative 2. Okay, now our points are also going to be affected because we need to consider what points we're actually allowed to have. So when we have these inputs of our, of our thetas, and we get our outputs of our radius, we want to make sure that the thetas that we put in are going to give us a radius that actually is real. And we know that in a square root, you can't take the square root of a negative number. So I see that my radius values under here are actually going to end up being negative, but we can't take the square root of a negative number. So in this case, we are actually not going to have any values in between there. So our radius values can only be positive. So that means that we actually have a limited domain that's going to produce those, okay? So we're only going to be able to graph between 0 and pi over 4. And then we're going to pick up again after 3 pi over 4. So there's no way I can put in or get out a radius value if I put in pi over 2, because that's not within the domain of this trig function anymore. Okay, I might extend this just maybe one more to maybe to 5 pi over 4, just to get me a little bit further. Again, if we need more points, we can graph more points. Okay, so because we know that our radius is from, we have a radius of 2, I might just change this graph so it's just not the smallest little symbol infinity that you've ever seen, propeller, whatever. Okay, here we go. So when I have a theta of 0, I have a radius of 2. So that's that point there. Okay, then when I have a theta of pi over 4, my radius is 0. Okay, so what's happened is that I have gone up here. Now, the next input that I can have is going to be 3 pi over 4, okay, which we know is 0 again. Then, when we go to pi, we have a radius of 2. So actually what's happening is this isn't graphing like a normal infinity, right? Infinities we expect to graph like this. Instead, this is graphing the top half, and then it's going to graph the bottom half, okay? So our next one would be 5 pi over 4. 5 pi over 4 is right here, and so that's going to end up graphing underneath. And then we're going to graph the underneath part as well. Well, okay, let's back up. You're probably thinking, well, hold on, how do you go? Yeah, wait, no. 5 pi over 4. It's going to be here, and then go here. Yes. Okay, so what ends up being our period? Well, that's a great question, because our period doesn't fully graph all of those points. Okay, so 5 pi over 4 got us back to 0, and then what would have gotten us back over to 2? Well, let's extend this out. Okay, so let's see. 5 pi over 4, 6 pi over, so 3 pi over 2 would have been here, and then what, 7 pi over 4 would have gotten us back to 0. Okay, so we're not going to have any of those values here. So 7 pi over 4 would have ended up here, and then this would have been 8 pi, so this would have been 2 pi, and then let's get there. Okay, so 7 pi over 4 is here, so 7 pi over 4 was back to 0, and then 2 pi got us back to 2. Okay, so this has a period of 2 pi, but we didn't use all of the radians within that 2 pi, right? We only used these specific radians, but it did take us 2 pi as a period to graph the entire thing. So we can say that our period is 2 pi. Just be aware that we didn't actually use all of those radius values, or those radian values. Okay, This was a lot, okay? There was a lot going on to it. So you're probably thinking, what are the important things that I need to know? The important things that I want you to know how to do when you get out of this, I'm obviously going to ask you to be able to graph some of these. But graphing them, as we can see, we're using the trig graphs from last semester in order to do that, okay? So I want you to know the way that they're graphed, okay? And I also want you to predict when you see the graph, predicting what those values mean and just predicting what the shape is going to look like. So before next class period, I want you to go through example 6, and for each of those polar curves, I want you to write out the different things that you know about it. Write out what the radius means. Write out how many petals it's going to have. Write out the type of symmetry it's going to have. We'll go over these next class period, but I want you just to be able to look at something and to know the basic shape. Okay, that's all I have for this video. I'm sorry it was a long one. I will see you all in class.